Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2023 chemistry exam for the Northern Hemisphere, part 1 of the short answer questions. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And anyway guys, let's smash through this video. Question 1. Kombucha is a fermented tea that is produced by mixing tea, water and sucrose with bacteria and yeast. The bacteria and yeast break down the sucrose. The yeast in the kombucha produces the invertase enzyme, which metabolizes the sucrose. So metabolizes means that it basically breaks it down, the sucrose present in kombucha. Name the type of reaction that breaks down the sucrose into simpler molecules. Now, we know sucrose is basically a disaccharide, meaning that it's two monomers of a carbohydrate, glucose, like this. We know to break down sucrose into its simpler molecules, we need to break down this carbohydrate glycosidic linkage. And to do that, we require water. And if we require water, this is a hydrolysis reaction. So hydrolysis. So hydrolysis is whenever you're looking at questions, if it's the breakdown of molecules like proteins, fats, or any macromolecule, when you're breaking them down, they go through a process called hydrolysis. But when you're forming them again from simpler molecules to actually larger molecules, this is called a condensation reaction. So just remember that if you're breaking molecules like sucrose or any sugars or carbohydrates or fats or proteins, they go through a process called hydrolysis. B. In the kombucha process, the bacteria produce cellulose, which is removed prior to bottling. State why removing the cellulose makes no difference to the nutritional value of the final product for humans. Easy. We know cellulose. We know humans can't digest cellulose. It's because we lack the enzyme cellulase. Remember cellulose, have you tried taking grass from the ground and eating it? You basically vomit it out quickly. It's because actual humans, lack the enzyme cellulase, which breaks down that cellulose. And so that's why cows and sheep basically have a lot of that cellulase enzyme, and that's why they eat actually grass and stuff, whereas, humans can. So overall, humans cannot digest cellulose because we lack the enzyme cellulase. That's it. And that's why it doesn't even make a difference in the nutritional value. If you can't digest it, you can't even break it down. You're just going to vomit it out. So absolutely. So, humans cannot digest cellulose as they lack the enzyme cellulase. Now, one of the coolest tricks that I've actually found that is if you look at the actual cellulose, to determine straight away its enzyme, it always has an A. You know how it says cellulose? The enzyme for it to break it down is called cellulase. Like for example, when you want to break down amylose, you use that enzyme called amylase. Starts with that A. So even like this one, it says invertase because it's an enzyme. So that's a kind of a trick into determining which are enzymes basically to break down. Beautiful. So humans cannot digest cellulose as they lack the enzyme cellulase. Beautiful. C. A kombucha manufacturer is considering adding vitamin C or vitamin D to kombucha. Explain the advantages of choosing vitamin C over vitamin D in your answer. Use understanding of chemistry that you have studied this year. Now, we know that vitamin C is a polar molecule. We know that. And it's in your data book. It's a polar, whereas vitamin D is a non-polar. They're saying basically, why is it an advantage of choosing vitamin C? Let's look. Because kombucha is made out of tea, which we don't know what tea is made out of, but it's mostly made out of water. Remember, water is a polar molecule, and sucrose, which is also it has a lot of oxygen binding site, so absolutely it's also a polar molecule. So if you're going to add vitamin C, it's going to be soluble in that kombucha and hence dissolve in it. Whereas if you use vitamin D, which is a non-polar, it's going to become insoluble. It's not even going to mix with it, and hence when dissolved in the tea. So that's why. Easy. So let's write that down. So say vitamin C is very polar. So very polar, and hence is soluble. So soluble in tea because the tea is a mix of water, they said, and sucrose. Which are both polar. Which are both polar. Whereas vitamin D is non-polar. And hence won't dissolve. And hence won't dissolve. Beautiful. Easy. Question D. Vitamins can act as coenzymes. Describe the role of coenzymes in enzyme reactions. Easy. So coenzymes, the best way to describe it is this. When you have an enzyme, let's say you have an enzyme, let's just draw a kind of a figure. Let's say you have an enzyme that looks like this. You can see that this is the active site of the enzyme. But and let's say this is your substrate. It's a square. Now we know if this, so this is your substrate. This is your enzyme. Now, if you know, we know that if we take this substrate, it won't bind to the active site of the enzyme because it cannot fit properly. So what a coenzyme does, it acts as a basically, in other words, if I can draw it, like make sure it looks, okay. What a coenzyme does basically is it attaches itself to the active site of an enzyme and basically changes its surface to enable this substrate to bind. That's what it's used for. So if I, like, for example, take this and now it's like nicely fits in there, and I mean, it's one of the best worst drawn, but then it perfectly fits into the active site now, and hence, you know, the enzyme can actually work on the substrate. That's one of the actual ways. And also, there's so many other things that coenzymes do. They basically can catalyze reactions. They can actually catalyze. They can act as a catalyst. One of also another forms is they can actually, they are carriers of atoms and electrons. That's another one that is a hint you can also have. So yeah, coenzymes have a lot of things. But basically, we just need, because it's 2 marks, I'm just going to say what we just said. So they are molecules that attach the active site of an enzyme and change the surface to allow the substrate to bind. And act as carriers of atoms and electrons. Easy. So I'm going to use a different color. I'm actually going to use this one. Okay. There are molecules that attach to the active site, of an enzyme and changes. So it changes the surface shape to enable the substrate to bind. The substrate to bind. And also another one that we said was a act. I'm going to write it. There's another dot point here. So it also acts as a carrier of atoms and electrons. Atoms and electrons. Beautiful. Done. Nice 2 marks. Question 2. Let's have a try this question here. Consider the reaction shown in the diagram below. All right, let's just go down to the questions. A. State the international union of pure applied to IUPAC systematic name of compound R. So here's compound R. So we can see it's an actual ester group. And remember, to name esters, like esters, this is what you do. You look on the alcohol side. Remember, because esters are made basically when you add an alcohol and an actual carboxylic acid. And when they react, this is what forms esters. We know that this part here is your carboxylic acid group because we can see that double O, that C double O. And this is your alcohol group. Now, to always name it, you always start with that alcohol group. We can see that there are 3 carbons in this side. 3 carbons, which is known as propane. You remember 3 carbons, propane. So we always start with the alcohol, and we're going to call it, it's going to be named as, because it's going to start with prop, because there's 3 carbons, so it's going to start with propyl. So if it had 2, you'll say ethanol, or if for example, if it had 1, you'd say methyl. Yep, so propyl in this case, and then you end up with the number of carbons of the carboxylic acid, which is 2, which is ethanoate. If it was 3, you would say propanoate. If it was, yeah, so that's how you end it with. So this is going to be ethane, no 8. Done. Very nice and easy to name ester groups, and ester. Name the functional group in compound M. Where's M? Here it is. This is M. So this is the functional group we can see. Be careful, this is not a keton. A keton is in the middle. Sorry, let me draw a nice. Is in the middle of. Can you see these carbons here? You can see it's only a C-double-O. It's a C-double-O. There's actually no hydrogens bonded to it. If there's hydrogen, no, and we can see, yeah, it's never at the end. It's never a C-double-O at the end. Because if it is, it's called an aldehyde, where basically you'll have a hydrogen here. And that's what this one looks like. We can see it's a C-double-O, and there's a hydrogen bonded to it. This is called an aldehyde. So easy. This is an aldehyde. Beautiful. So, aldehyde. Next question. Identify the reagents required to convert compound M. Where's M? So this one here. So identify compound N to compound N in the box provided. Okay, compound N, which is this part here. All right. Now, what do we know? Well, okay. We can see that when we're doing this part here, we can see, okay, we use UV light and then we add it with water. So, okay, no, this here is the alcohol. Remember how to make sure you form like an ester, you need an alcohol and a carboxylic acid. This is here the alcohol pathway. Okay, it's creating the alcohol. So hence this part here must be the carboxylic acid. So we're going basically from like an aldehyde, which is from here, to a carboxylic acid. Make sure you remember the pathways. I'm going to show you, here is the pathways if you don't know. This is a nice diagram that describes it. So basically we are going from compound N, which is an aldehyde. So here's an aldehyde. And we are going basically forming a carboxylic acid. So going to the right, there's the carboxylic acid. And here is the reagent that we use. So let's start reagents there. So it's a CR2O7 2 minus aqueous / H plus aqueous. Make sure you have these on your, make sure you memorize the pathways. They are so easy to memorize, but I have them here so you can guys see what I'm looking at. Beautiful. Hope that makes sense. So, okay, we've done that. Let's come back. So did we answer the question? So identify the reagents. Yep, in the box. Beautiful. These are the reagents. Next thing, draw the structural formula of compound N in the box provided in the diagram above. Beautiful. Easy. So remember, when it reacts, this is going to form a carboxylic acid. So when you form it, so it's going to be C-double-O-O-H. Done. It becomes a carboxylic acid. Done. All right. What is the name of the reaction type that produces compound Q? So compound Q here, we're going from basically propane. So C, propane. And we're reacting with chlorine, 2 chlorine, so chlorine gas. Now, what's going to happen? We know that what's happened. So it's with UV light. So looking at my reaction pathways, we have an alkane, and you can see that reacting, like for example, here is bromine, there's bromine gas, but we're still reacting with UV light. So it's the same as chlorine basically. And what happens is basically one of the hydrogens just gets replaced with one of the chlorines. So it basically is a substitution reaction, because what are we doing is we're not adding all of it. Look at this. We're actually just substituting one of the hydrogens with one of the chlorines. And so basically, you'll be left out with hydrochloric acid, HCl after. So yeah, you just basically took one of the chlorines from one, switched over the other. So this is just a substitution, not an addition. Easy. So a substitution reaction. So substitution reaction. Done. Compound Q is converted to compound M. So Q to, yep, okay, compound P, when reacted with water, all right, makes sense. Compound P then reacts with compound N to produce R. All right, makes sense. Draw the skeletal formula of the compound Q in the box provided. So Q, all right, that's easy. We've actually just sketched it right here. This is how it looked when it goes through the substitution reaction. So we have two C's, so 1, so 2, and 3, so 2 carbons, and a Cl here. So basically it will look like this. This is what it will look like. Easy. In its skeletal structure. Does the compound Q have a chiral carbon? Justify your answer. Let's have a look. Remember, for it to be a chiral carbon, the carbon has to have 4 different groups around it. So here, look at this. Let's look at this carbon here. This carbon here. We can see that they have 2 of the same, like they have hydrogen and hydrogen. So the groups, nope, that doesn't work. Also the same with this, and also the same with this. There are not there's no 4 differently, groups around it. So yeah, compound Q does not have any chiral carbons. Because it's 2 marks, we do have to write some stuff. So we would say no, and we say because, and we'll just describe what the definition for a condition for carbon to be a chiral, because you remember 4 different groups must be attached to it. So for carbon to be chiral, for different groups must be attached to it. Beautiful. Done. Next question. This is green here. A galvanic cell can be constructed from nickel to aqueous nickel solid half cell and Ag plus aqueous and Ag solid half cell. State the maximum cell voltage under standard conditions of this cell. Okay, easy. So let's just highlight them in our electrochemical series. So we have nickel 2 plus and nickel solid. We also have Ag plus and Ag solid. So remember, we need to first determine which one is the strongest reducing or the strongest oxidizing agent. And to do that, it's always on the left and it's the highest one. So looking on the left, it's this one. So Ag plus is going to go basically through reduction, and it's going to, so basically go this way. All right, and which one is the strongest now reducing agent, which is the one that's at the bottom on the right, which is nickel. So it's going to go, it oxidizes to make this here. So the ones that are reacting is this half cell and this half cell. So remember, to get the actual voltage, it's just minusing those voltages, which is basically 0.80 minus negative 0.25. A hint, it's always start from the top minus the bottom. That's the rule. Which gives us what? Do a calculator. 0.8 plus 0.25. Which is 1.05 volts. 1.05 volts. Done. Write the overall equation for Ag plus and the nickel salt galvanic cell. So the galvanic cell, easy. Well, all we need to do is basically, let's write the actual reactions that we said. So Ag is basically going to reduce, so Ag plus, let me write them nicely here. Ag plus aqueous plus electrons goes to, reduces to Ag solid, and we said that nickel is going to oxidize, so nickel solid oxidizes to 2 electrons plus nickel 2 plus aqueous. Done. And so now we know this. We need to make sure to get the overall reaction. Remember, these are your 2 half cells. To get the overall reaction, like the equation, you need to make sure the electrons are the same. So I'm going to multiply everything here by 2. So to make this electron also 2. So I also have to multiply this by 2. Done. So now we're going to cancel those electrons and add these reaction together. So it's going to be, looking at this part here, this is going to, so it's 2 Ag plus, let's write that down, 2 Ag plus aqueous plus nickel solid, that gives us overall 2 Ag solid plus nickel 2 plus aqueous. Nickel 2 plus aqueous. That looks very, very good. Done. finished. Let's move on with the next question. Microbial fuel cells. Okay, this is actually a fuel cell that needs to be known in the new study design. If you haven't actually seen the new study design, the 2024, those who are doing the 2024 exams, this is in your study design. You need to know what a microbial fuel cell is. MFS, basically MFC, which is microbial fuel cells, use bacteria to metabolize biomass. Remember, so bacteria is basically breaking biomass out. And biomass is basically produced from like plant waste or, just a waste of most of plants and or like the poop of sheep and stuff. Basically, these are all waste of bio. In an MFC, so microbial fuel cell, the bacteria decomposes biomass easily. So it breaks down biomass in the absence of oxygen through a process called anaerobic cellular respiration. Easy. So for basically what it's saying is for bacteria to break down biomass, it needs to have no oxygen. It has to have the conditions for it must be no oxygen, and hence it goes through anaerobic cellular respiration. If it did have oxygen, it goes through a process called aerobic cellular respiration. Then that's what us humans actually go through, aerobic, not anaerobic, because we require oxygen. Write the equation for the respiration that occurs in the human cells of the body. Beautiful, easy. So remember, we go through something called cellular respiration, where basically glucose, the most basic unit of a monosaccharide, of carbohydrate, glucose basically oxidizes, or in other words, combusts. So we know that glucose, memorize this formula. It is so easy. So I think a lot of bio students have memorized this formula because I think you require that. So basically, remember cellular respiration formula. So it's basically your glucose, which is C6H12, oxygen 6, AQS, and it's AQS, plus 6 oxygen gas molecules, and they form 6 H2Os, and these are going to be in liquid state, and 6 CO2 in its gaseous state. And this is your actual cellular respiration formula. And you can see that we require oxygen for us to basically, so we go for aerobic cellular respiration. On the axis below, sketch the energy profile diagram for respiration. So it's only 1 mark, so you just want the shape of it. Now, easy. We know this here is a combustion reaction, like what we said. Remember, you're reacting a fuel, in this case, which is oxygen, your glucose, with oxygen gas, and hence we're producing CO2 and water. So it's basically, this is an exothermic reaction. So it's going to look like this. For exothermic reaction, it's going to look like this. Done. Easy. Okay, the MFC anode has bacteria growing on it. And so the bacteria decompose organic matter and produces H plus ions and electrons. The bacteria transfers electrons directly to the anode. One half cell has oxygen bubbled into it. In the other half cell, oxygen is excluded, so no oxygen. A diagram of the microbial fuel cell is given here. Easy. So what we see here is this has to be your anode. Because this is your cathode, this has to be your anode. And you can see that basically they said that bacteria is growing. And basically this bacteria is basically breaking down biomass and it's producing these H plus ions. Remember, you need to know some knowledge of the microbial fuel cells. So we know this part here is a proton exchange membrane. So basically it only allows protons to move, not electrons, not ions, not anything except H plus ions, which is our protons. So this part here is called a proton exchange membrane. Beautiful. And we can see that the anode, and we can see that they're basically separated. Of course, they must be separated because look, we're feeding oxygen gas to the on the cathode side, whereas of course bacteria is on the other hand side. And for bacteria to work properly, to break down, it has to have no oxygen. Like we said from the other question, it has to have the absence of oxygen to go through anaerobic respiration. So absolutely, that's why we have this membrane that basically blocks them. Easy. Write the balanced half equation for the reaction occurring at the cathode. Easy. So basically we're reacting oxygen gas, and these H plus ions are going to be coming to it. And if these H plus ions, so imagine you're reacting oxygen gas and we with plus H plus ions plus electrons, because electrons are going to go from the because this is your anode. Remember, your anode's your negative charge and this is your positive, because it's the fuel cell. So electrons go from the negative to positive, and hence, which equation has all of these? Easy. We have it in our formula sheet. Have a look at that. This one right over here. This is the perfection one here. This one. Oxygen gas plus 4H plus, it's this one over here. Remember, oxygen gas is reacting with those H plus ions that are coming from the anode to the cathode, and the electrons that are basically getting received by the cathode. And so we're forming water, which is what this shows. This is perfect. So this is the reaction at the cathode. So, and remember, the cathode is where basically our reduction occurs. So we write this equation here. Very easy. It's 4H plus aqueous plus 4 electrons gives us 2H2O in its liquid state. Done. All right, so that is good. Next question. Explain why the two half cells are separated. Like we said, first, let's talk about the most basic thing. It's an actual galvanic cell. If you take those two reactants and react them together, imagine that we didn't have this separator. These two reactants will come together and basically go through a spontaneous reaction, and we won't actually produce a circuit. Remember, we won't produce it. That's why we separate it, so we can get electron flow, and that's what creates electricity. But if that proton exchange membrane was not there and they weren't separated, of course they will those reactants will come and basically go through a spontaneous reaction. Basically, we're doing this energy conversion of chemical energy straight away to thermal energy. It's just going to basically produce heat, not electrical energy, and that's not what we want. So that's rubbish, because that's just a waste of actual chemicals. Put those two chemicals in producing thermal energy, which is useless energy, to be honest. In this case of this, we want to produce electrical. So that's one of the big problems. You don't want to mix them, because there will be a spontaneous reaction, changing the energy to heat. And also another one is what we just said. Bacteria requires no oxygen, basically to decompose. And so if you basically didn't have this proton exchange membrane, you're going to get oxygen on the anode side. And so if there's oxygen on the anode side, your actual bacteria now has oxygen. And remember, if it has oxygen, it doesn't work properly. It's not going to go for anaerobic respiration and break down that biomass. So absolutely, that is why. So it's 2 marks. I'm going to write those two things that we just said. So very nice actual question. So we're going to say, basically, we want to prevent mixing of reactants from two half cells. So prevent mixing from two half cells, which would lead to a spontaneous dissipating as heat energy, not electrical. There it is. So prevent mixing of reactions from the two half cells, which would lead to a spontaneous reaction, dissipating the heat as heat energy, not electrical. And that's what we want. We want electrical, not heat. And also, like the other one, what we say bacteria requires no oxygen. I'm going to say oxygen gas to basically, so it requires no oxygen gas to decompose, how do I spell that? So pose bacteria. If cells come together, O2 gas basically will move to the anode side, and hence bacteria won't work properly. Hence, bacteria won't function. Properly. Probably. If that makes sense. Did I write it nicely? Like, prevent mixing of the reactors from the two halves, which would lead to a spontaneous dissipating heat. It's not electrical. Bacteria requires no oxygen to decompose. If cells come together, O2 will move to the anode, and hence bacteria won't function properly. Beautiful. Let's have a look at F. For the cell shown in the diagram, state the feature that causes the overall movement of H plus ions across the membrane. Explain your answer. I mean, this is quite easy if you're a bio student, because I think we know something called about a concentration gradient that I'm looking at. So because I'm looking at this here, the only thing that I kind of think is how this will produce a concentration gradient. Let me explain. What are we actually answering? So a feature that causes the overall movement of the H plus ions across the membrane. So why does the H plus ions move across it? Let's think. Let's got this out. Okay. So because this, on this bacteria, it's going to be producing H plus ions. Imagine we have all these extra H plus ions. We have a lot of H plus ions in the left-hand side and the anode side. Basically, what this means is on the left-hand side, we have a very high concentration of H plus ions. And remember, this is what's going to create, it's going to create like a concentration gradient. Remember, we have this proton exchange membrane that only moves H plus ions, nothing else. So if we have a high concentration of H plus ions and we have a low H plus ions concentration on the cathode side, what's going to happen? Diffusion is going to occur where basically where H plus ions want to go create equilibrium. So if they're basically all going to diffuse, because remember what happens is this creates like a concentration gradient where basically where ions from high concentration go to low concentration. So all these H plus ions will try to move to the right so they can bring this to equilibrium. So it can have also the same H plus ion concentration too. And so if it does that, there is equilibrium reached, and hence the concentration gradient will be 0 again. And that's what it actually achieves. This is what it achieves, basically. That's what diffusion is. So in terms of bio, I'm thinking this is one of the best ways to explain it. We have very high concentrations here, and then we have low here, and so they basically diffuse because they're going from high to low concentration. And that's all I can think of because I'm trying to think of like other ways to explain it. But in terms of bio, that's what we would kind of explain here. So, yep, I hope that kind of makes sense. So, explain your answer. Let's do that. Okay, so basically what we're going to say, it's on the anode. Yep, so on the anode side, there is a lot of H plus ions, whereas at the cathode, there isn't a lot. There isn't a lot. This creates a concentration gradient. This creates a concentration gradient. Across the proton, proton exchange membrane, that drives the movement of H plus. So the movement of H plus ions from anode to cathode. Beautiful. And I think that is like the most suitable kind of, to answer this question because, there's a concentration gradient that will be created. Beautiful. If that makes sense. G, state an advantage of microbial fuel cells over this galvanic cell. Of course, these are metal. This is the most easiest part. You're using a microbial fuel cells. Basically, you're using biomass, which is waste. And basically, you're creating energy with it. This is very renewable. First, it's very renewable. And we have so much of it. We have so much biomass that is waste. Which basically makes this, this whole fuel cell very sustainable. Because basically, imagine converting waste material into electricity. That is very good. Whereas, the Ag and the nickel one, galvanic cell, it does, but the problem is you require metals, you require metal electrodes, ions, which are basically could be expensive because they're not like, of course, biomass is very easy to find, but you have to basically purchase, metals and stuff like aging, so it's very expensive, and it's not renewable. These stuff like nickel and stuff, these are not very formed easily compared to biomass, which is just basically, so absolutely, in terms of expensivity, it's using, biomass is so much times 10 better because it's more renewable. So 1 mark. So let's write down, okay. In the MFC, uses biomass. So let me just actually write just biomass. I think it's not too much. So biomass is renewable. Biomass is renewable and readily available. There's a lot of it available. This makes MFC sustainable. Basically makes it sustainable as it converts waste material to electricity. Waste material to electricity. So in comparison to the other one too, so Ag/nickel basically cells relies on metal electrodes and ions too. And ions that are not renewable, and can be expensive. Beautiful. Done. Question 4. Let's have a try at this. This is a nicer color. Let's use this color here. A bomb calorimeter has a calibration factor of this. The calibration factor was determined by using an electrical heater operating at 240 seconds at 6.5 volts. During the calibration, the temperature increased by 1.17. So 1.77 degrees. Calculate the current that's passed through the heater. Easy. So we know that calibration formula is voltage, current, times time over change in temperature. We're basically given everything here. So we know that the calibration factor is 3,540. The voltage is 6.5. The current is what we're trying to calculate times your time in seconds. So 240, all being divided by that change in temperature, 1.7. So basically, if I'm calculating this, I should get, so 3,540. Okay, so 3,540 times 1.77, and then we divide that by 6.5 times 240. We get a current of how many significant figures? 3. So 4.02 amps. Done. A 2.5 gram sample of muesli was placed in a calorimeter and completely burnt. No significant amount of ash remained at the end. This is great. So if there's no ash basically left out, this is good because it tells us that a complete combustion has occurred. Because if there was ash, ash is in other words for soot, which means that if there's an incomplete combustion, which is not good. It means not all of the energy basically was given out. So beautiful. The temperature increased by this. Calculate the energy content in kilojoules of 100 grams of a muesli bar. All right, so what are we going to do is we have the calibration factor, so which is what? 3,540, which is equal to joules, basically your energy over your change in temperature. So your degrees Celsius. Now, if we know that the temperature was measured to be 5, so we put 5 here. So the energy is, so what's 540 times 5. So the energy is actually 17700 joules. Make sure to convert it to kilojoules normally. So divided by 1,000. So it's 17.7 kilojoules. Meaning that if you burnt 2.5 grams of a sample of muesli, you should release 17.7 kilojoules. Now, good. But we want to find how much energy, what's the energy content for basically 100 grams of a muesli bar. So to do that is, we're going to use ratios because what I'm going to think is this. I'm going to use ratios here. Put an equal sign. Okay. We know that when we basically burnt 2.5 grams of muesli, we released this much energy. 17.7. And if we're basically going to burn 100 grams, how much energy? So X, how much energy would that release? So we get this nice ratio, and we just have to calculate X. So basically what's that going to be? So what's first? 2.5 divided by 100, which is 0, so 0.025, 17.7 over X. And so basically if you flip these two here to get X now, you should get 17.7 divided by that. We get 708 kilojoules. So let me move that there. So we get actual in terms of energy, 708 kilojoules. So basically, if you burn 100 grams of muesli, you should release 708 kilojoules. 20% of the energy content of muesli is due to the protein present. Calculate the mass of the protein in 100 grams of muesli. Easy. So if we know that in 100 grams we release this much energy, and we know only 20% of that energy is actually protein, so let's multiply by 0.2 to see how much energy the protein would release. Times it by 0.2. We get 141.6 kilojoules. So basically, when you eat 100 grams of muesli, you basically get 141.6 kilojoules from the protein itself. And so to calculate how much mass of the protein was, easy. If you look at your what we call data book, what is the kilojoules of protein? There it is. Protein here releases, for every gram you release 17 kilojoules. So basically, let's write that down. So 17 kilojoules for basically kilojoules over gram. Oops, take that. All right, so here's our formula basically. So if we have basically in every gram we for every gram we basically release 17 kilojoules of energy. So if I replace this kilojoules with the kilojoules that we have, which is 141.6, we can actually calculate the grams. So grams would be 141.6 divided by 17. And that gives me, how many significant figures? We use 17, which is the lowest, so just 8.3 grams. So it will be 8.3 grams of the mass of the protein. Beautiful. When muesli is consumed, it is metabolized by the body. State how the products of metabolism are used by the body to produce large biomolecules. Easy. So look, when we eat something like protein or carbohydrates or anything like fats, what we have them in actual large molecules that are basically, we call these polymers. They start off polymers. They're all bonded together. And basically when we consume them, we use hydrolysis to break those bonds and make them into simple molecules. And so basically, okay, we have those simple molecules in our body, but when our body is of course, it creates proteins for function, cellular respiration. It creates, so basically what it does is, the products of metabolism, which are your basic units like amino acids, your monosaccharides, all these basic units. So we want to say how the products of metabolism, so those are used by the body to produce large biomolecules. Easy. So you know how we basically broken them down into basic monomers? How does our body basically make them into larger biomolecules? So bring them back to, if amino acids, we want to basically put them back together to make them proteins, or monosaccharides, we put them back to create carbohydrates. How do we put them back? They go through something called a condensation reaction. So remember, condensation reaction is where water is released, water is taken out, and basically they form, again, bonds. And that's what they go. They go through condensation reaction, and they all come together, and so now they form, again, a polymer, basically. Easy. So remember, a monomer is when you have one, a polymer when you have multiple, when they all form together. So, yeah. I hope that makes sense. So, I think because it's all in one mark, it's talking about how the products, condensation reaction. We're talking about a condensation reaction here. Are used to produce large molecules. So they go through a condensation reaction. And that's for all of the amino acids, so your proteins, your fats, your carbohydrates, all of these go through that. The product of metabolism, such as amino acids, so your protein, amino acids, fatty acids, which are your triglycerides, breaking the fatty acids, for example, glucose, which is your basic unit of carbohydrate, glucose, are all monomers. And these are monomers. And so they go through condensation. Reaction. Condensation reaction to form large biomolecules. Large biomolecules, which are also, and these are basically called, and they basically form like polymers. Form polymers. Easy. Other than the chemical produced by metabolism, so of course when you metabolize, it means they're breaking down. Let's say this is your carbohydrate. You have all these, and so other than the chemicals produced by metabolism is the breakdown, so when you break these down, what else does metabolism provide the body? Easy. So think about it. It says that when you metabolize, you're breaking down those bonds, and hence these are your chemicals. But if we're saying otherwise, what else do they do? When you break down those bonds through hydrolysis, you're releasing energy. Remember, those bonds carry a certain amount of energy, and every time you break them down, hydrolysis is an exothermic reaction. It releases energy, and that energy is taken by the body, and that's why we eat food. That's why we eat food, because when we break it down, we take energy in terms of ATP, and especially if you do bio, and yeah, that's what we use it for. So other chemical. So what else does metabolism provide the body with? Energy. Don't use ATP. Don't write ATP because that's not part of the study design. They didn't teach you that, but that's only for bio students. Yep. Easy. Question 5. Let's have a look at this here. A student wrote the following partial experimental report. Luminol is an organic molecule that produces light when it oxidizes. It is used in glow sticks. Luminol oxidizes when it reacts with sodium hypochlorite. So light sensors can be used to measure the intensity of light hitting a surface. The amount of light is measured in lumens, and the light intensity is measured in lumens per square meter. To investigate how oxidation rate of luminol is affected by temperature. Easy. So your RAM, we already know what our independent variable is, how it's affected by temperature. So this is your independent variable, the thing that you're changing, manipulate, and we're basically trying to measure the oxidation rate of luminol, which is our dependent variable. Materials, so sodium hypochlorite solution and luminol solution. Apparatus. Okay, the reaction vessel is sealed and its inside surface is black. It has a detachable black lid that contains 3 rubber-lined holes. The holes are sized to exactly fit a thermometer, a pipette, and a light intensity sensor. Okay, this all looks good. Method. Add 200 milliliters of luminol solution to the reaction vessel. Clamp the lid over the top of the reaction vessel. Place the reaction vessel in a water bath at 10 degrees Celsius. Put a thermometer into the luminol in the reaction vessel through the appropriate hole in the lid. Put the light intensity sensor into the top of the reaction vessel through the appropriate hole in the lid. Place 100 milliliters of sodium hypochlorite solution into a beaker and place the beaker into water bath 2. Okay, 7. When the temperature of sodium hypochlorite solution and luminol in the reaction vessels have both reached 10 degrees Celsius, rinse 400 milliliters of the pipette with sodium hypochlorite solution. Alright, that's good. That's good. Fill the rinse pipette with 40 milliliters of sodium hypochlorite solution and put the pipette in top of the reaction vessel through the appropriate hole in the lid. Push the pipette plunger to put that sodium hypochlorite solution into the reaction vessel, and at the same time start the data logger for the light intensity sensor. Repeat the steps using 30 degrees water bath and 40 degrees water bath. Beautiful. This looks good. Alright, makes sense. Okay. And these are the results. Light intensity versus time for the luminol reaction at different temperatures. Alright. So we can use a higher temperature. We can see it reacts quicker. The light intensity is very, very higher. Meaning that, and it finishes quicker. It comes to complete. So if the light intensity becomes 0, it means basically there's no more reactants that are forming, and the reaction has come to completion. So so the higher the temperature, basically the faster the reaction rate. In other words, the faster the reaction rate because it finishes quicker. And we can see also the 30 degree a little bit. You can see like it finishes at around 10, whereas the 10 degree one is, of course, it takes 35 seconds to come to completion. Easy. That makes sense, of course, because remember, temperature increases reaction rate. How can the graph above be used to compare the reaction rate at different temperatures? Easy. Let's talk about some stuff that we can use to compare the reaction rate. One of the best ways is the gradient. It's always one of the best things to use to kind of measure the rate of reaction. Have a look at the gradient of the 40 degree one. Its slope is very, very steep. It's so steep, meaning its reaction rate is very, very high. Whereas for the other ones, of course, it's getting lower. You can see the steepness is becoming lower. And of course, for the 10 degree one, you can see it has a very low reaction rate because it's much more less steep. Its gradient is very basically It's smaller. So yeah, in other words, we can use our gradient. We can use the initial gradient of the graph, that initial gradient, to basically determine which one has a faster reaction rate, which one has a greater reaction rate when those reactants are mixed. Another thing, because we want, it's 2 marks, I don't think that will give you, another thing. Another thing that we can talk about is the time actually taken for the intensity to come back to 0. Doesn't that make sense? So think about this. Think of that 40-degree one. So, okay, the reaction basically goes and it comes back and it finishes here at 5 seconds. So the intensity comes back to 0. So if we know when the intensity comes back to 0, that's when the reaction has gone to completion. And remember, the faster it gets to completed, the faster. So the shorter the time, the faster the rate of reaction, because the reaction has gone quicker. For example, look at the 10-degree one. It has a very, very, very large time. So it's a very large time, means the reaction rate is very, very small, because it takes very long for the reaction to complete. So yeah, these are 2 ways that you can look at to measure the reaction rate at those different temperatures. Yep, let's write those down. So we can use the initial, the initial gradient. And one of the best things about the initial gradient, you can actually use it for if this was concentration time graph. Or look, I'm not gonna lie, there's actually like a very thing that I've learned. If you have a time over whatever, if it's concentration, this is mass, but if this is time on the x-axis, it's always like normally it tends to be like the gradient that tends to kind of determine the rate of reaction. So that's a hint. For example, when I saw time here, I realized straight away, if it's light intensity, the gradient is going to be very useful to determine the rate of a reaction. So the initial gradient of the graph, so that initial indicates the reaction rate. So the reaction rate after basically the reactants are mixed. Done. Another thing is that we said the time taken for the intensity to reach 0. So the shorter the time means the faster the rate of reaction is. The rate of reaction. Beautiful. Let's have a look at the next question. So B, it says the graph of page 25, so this one here, shows the experimental results for the first 35 seconds from the moment the solution of hypochlorite is first pushed into that reaction vessel. Describe how the reaction rate of the reaction mixture at 30 degrees changes over time over the 35 seconds. Explain why these changes occur. So 4 marks. So basically just describe it and we'll explain why. Let's just think of in terms of like the reaction rate. Like explain it using like, the reaction rate, how the reaction rate. Yeah, so let's just basically look at it. Okay, we're looking at the 30-degree one. So what do we see? Well, we can see that from starting from 0 to, this looks like 3 seconds. So from 0 to 3 seconds, we can basically see that this intensity rapidly increases. So it rapidly increases, meaning that we have a very high initial reaction rate. So we have a very fast reaction rate from 0 to 3 seconds, and that's makes sense because you've started off with high concentrations of luminol and sodium hypochlorite. That's when you're starting with. You have high concentrations before you start even the reaction. You have them basically at high concentration, and when you mix them together, they're going to be colliding with each other. They're going to be basically, the frequency is very high, hence the reaction rate is initially very quickly goes up. So yeah, because as again, luminol is basically getting oxidized by that sodium hypochlorite. So makes sense. So that initial from 0 to 3 increase in reaction rate is because we have high concentration of both luminol and sodium chloride. So we can say that, of course. And what about that? When we reach that peak, at 3 seconds, basically this is, after that, we can see that there's a decrease in the, in other words, in the light intensity, meaning that the reaction rate is slowing down. It's slowing down. And it makes sense because what happens is the reactants are starting to deplete. They're starting to finish. So when they're starting to finish, of course, if this tells us that basically the reaction is coming slowly to an end. And we can see that then it starts to like narrow, becomes like what we call it is, it's like leveling, or it's coming to a plateau. And basically this basically tells us that the reaction is nearly to completion. So it's getting to completion. And it makes sense because the reaction rate is becoming so low that because of the luminol, luminol? Because the luminol is basically is getting oxidized. Like, it's mostly oxidized now. So that's why basically the reaction rate is very low, because most of the luminol has been oxidized, and yeah, it's becoming steeper and steeper, and then reaches at 35. The intensity becomes 0. So the reaction has been done. It has been finished. I think that's all you just like talk about. I'm not gonna lie, for the 4 marks. Just describe it, and with the way we describe a reaction rate, the different parts of the reaction rate for the timing. But 4 marks is a lot. Damn. Just gonna write. So we said the intensity. So the intensity rapidly increases during the first 3 seconds. This was due, we said this was due to the high concentrations, remember, of both of the reactants, the luminol and sodium hypochlorite, or what the hell? Hypochlorite, yes. So the intensity rapidly increases during the first 3 seconds. This is due to the high initial concentrations of both reactants. So reactants, which hence increases the reaction rate. The reaction rate as luminol is oxidized by sodium, can be bothered, so sodium hypochlorite. Hypochlorite, yep. So, okay. Also, then after, at the peak, it starts to decline. So, the intensity reaches its peak at 3 seconds and starts to decline. This is due to the reaction rate slowing as the reactants are starting to deplete, starting to finish, or deplete sounds better. Deplete. And the reaction is coming to a finish. Is coming to a finish. Beautiful. And I wanted to write more because I was like, we talked about how it was reaching that plateau. Yeah, we want to also write that. So I want to just make a little bit extra space for this. Well, it is 4 marks. I don't think that this maybe give you like, it will give you like still enough, but I want to make sure we get into detail more. Also, what are we going to say? We will say, when basically the intensity decreases and levels off, indicating the reaction is near completion. So they're indicating the reaction is near to completion. So its reaction is near completion. And basically, this is due to the reaction rate becoming very low. Very low, as most of luminol would be basically oxidized, of course. Luminol has been oxidized. That is it. And that kind of gives the full mark. I'm not too sure, yeah. Hope that makes sense. Would it give you that full 4 marks? Don't know. Really, that's a little bit an ugly one. Just write it like this. Alright, that's it. C. Write a conclusion for this experiment that is consistent with the results shown on the graph on page 25. Easy. One of the most easiest ways. I love when it says conclusion, because conclusions in chemistry don't have to be very detailed. They can be the most simplest. Normally, they're always 1 mark. Remember, for conclusions, all you need is this. You need to refer to the independent and dependent variable and what the results were telling us. We know that as you increase temperature, what happens? The reaction rate increased. So, you just basically say this. In conclusion, by increasing temperature, the oxidation rate of luminol increased. So, that is it. It's very simple and nice. You just need to include those variables. So, use this. In conclusion, increasing temperature. So temperature increases. What was it? Increases what? The oxidation rate of luminol. Increases the oxidation rate of luminol. That is it. Very nice and simple. Goes to the point. Question D. State 2 possible sources of error for this experiment when answering the question. Assume that the experiment method is followed correctly and the equipment is calibrated accurately. Okay, this is one of the most common kind of questions to see error in the experimental method. Now, I don't like when they say we can't use the equipment calibrated, because it just like a little bit limits us. It's a little bit kind of, yeah. So we need to see some errors that could have occurred. Let's go back. I think one of the best ways is kind of rereading it. Experimentally has been detachable backlit. The holes are sized to fit the thermometer, a pipette and light intensity sensor. Actually, one error that they actually could have had is, think about it. So you know how basically they had that sodium, what was it again? Oh my god, my full brain's gone. Sodium hypochlorite in the pipette when they were basically pushing it into the when they were putting it into the luminol here, they had no stirrer, so the thing that stirs it up. So basically that sodium hypochlorite could have been in the on top of it, and it wasn't like mixed around the whole thing uniformly because there's no stirrer. Now they're not actually stirring it; they just put it in. So that is a big problem because that means that it's not like the sodium hypochlorite is not like uniformly mixed around the whole luminol, meaning that there's like this, the concentrations are inconsistent at different places. So again, if there's inconsistent in concentration, that would of course affect the reaction rate because concentration is dependent on reaction rate. If you have high concentration, the reaction rate increases. So that could have been a big problem. They didn't actually stir it up. So we can say that is a problem. That is actually good. And we also need one more. So add 200 luminol solution to the reaction vessel, clamp the lid, place it on this, put a thermometer into luminol for the appropriate hole in the lid, put the hole intensity there. Okay, and the beaker is in water bath. When the temperature of the sodium hypochlorite, it's actually quite hard when the sodium mineralized and luminol in the reaction vessel have both reached this. Rinse a pipette with sodium hypochlorite. Okay, that's correct. Fill the rinse pipette with this and sodium hypochlorite and put the pipette in the top of the reaction vessel through the appropriate hole in the lid. Look, I'm gonna look at the most smallest kind of detail here because I have no idea what the extra, another error could have been. Okay, I think I'm just looking at the most smallest thing that I can try to finish the question. So this pipette, you know the pipette? So they used a pipette that was at room temperature because they didn't do anything. So imagine, okay, you have your sodium hypochlorite solution, which is in that water bath, and say it's at 40 degrees Celsius. If you're using a pipette that's at room temperature, so at 25 degrees, and when you basically suck that sodium hypochlorite, when you basically take it, it's gonna affect the temperature because you've got the pipette is at 25 degrees, and whereas the sodium hypochlorite is 40 degrees, it's gonna basically decrease the temperature of the sodium hypochlorite. It's not gonna be absolutely now at 40 degrees Celsius. I'm just looking at the I'm just trying to look at the most because I'm very struggling to find another error. It looks very good, this whole experiment. But yeah, that could be like an error. So like the heat exchange between the pipette and sodium chloride, because they're not at the same temperature, and because if the temperature, let's say, slightly decreased, that would of course affect the reaction rate. And so I'm just gonna write that. I hope that should get them. I hope if it doesn't get them, I'm not surprised. But yeah, it's kind of going in detail. I have no idea what other else ones I'm looking at, because I was looking at the pipette. But then I hope they, like, I was wishing that they actually, let's say they said they mixed, like, they washed it with water and it would make me so happy, but they actually did the right procedure by rinsing it with the sodium hypochlorite solution. So, damn, they really don't have a lot of errors in this. So, I'm just going to use that, actually. So, let's write those. So, we said basically how there was no stirrer and it wasn't uniformly mixed, we can say that, and how the heat exchange between the pipette and sodium could have affected the temperature, which would affect the reaction rate. So we just need two of them. Let's do that. So the first one we said the sodium hypo. We said the hypochlorite was not uniformly mixed with the luminol, as there was no stirrer. So stirrer, I think that's how you spell it. This can lead to an inconsistent concentration of reactants, which would affect reaction rate. Beautiful. Let's now talk about the pipette one. So there could be some heat exchange with the pipette and the sodium chloride. So sodium hypochlorite. So hypochlorite as the pipette. So as the pipette is not the same temperature. As the sodium hypochlorite, as the sodium hypochlorite. This would affect the temperature. This would affect affect the temperature. So this would affect the temperature and the reaction rate. Perfect. I hope that makes sense. I think, look, the first one makes sense. Like, I really genuinely think, yep, not stirring it up properly. But the last one, where we're talking about the heat exchange, I've been just trying to look at the smallest detail, which is not kind of, because there isn't a lot of errors that I saw in this experiment. But I hope you guys enjoyed this video and learned something through it. I hope it made your life easier and learning in chemistry. And please take care of yourselves. I hope you guys have a great day. Bye-bye.